Okay, I think we can continue this afternoon session with Srinivas Raghu. We'll talk about quantum Hall to insulator transitions with interaction and disorder. Please.
Thank you very much for asking me to speak. I would much rather be there in person. I'm sure the coffee there is much better than what I have at home, but nevertheless, here we go. I'm going to speak on the problem of quantum Hall to insulator transitions. And it's one of these amazingly beautiful problems in theoretical physics, which still remains unsolved, and there's lots to be done. The talk I'm going to be giving is a culmination of several papers from 2018 until this year, done mainly with my former student Prashant Kumar, shown here. Can you guys see my mouse, the cursor? I assume yes.
Yes, yes. Very well.
And a student named Pavel Nosov, with whom I've been thinking about this, and a former undergrad who's now a graduate student at Princeton as well. And so here's the problem. You take a 2D electron gas, you put it in a magnetic field, you change the magnetic field, and you change the ground state from, say, an integer quantum Hall state or a fractional quantum Hall state to an insulator or other quantum Hall states. So the tuning parameter for the critical phenomena is an externally applied magnetic field. It's a two-dimensional system. The quantum Hall phase only is strictly defined at 0 temperature. So there's a quantum Hall phase, there's a quantum critical point giving way to an insulating state. Okay, so that's the phenomenology. And the nature of the quantum Hall state can either be integer or fractional. So just to give you a sense of how primitive some of our understanding is of this phenomena, let's think about the integer quantum Hall effect. Usually when you ask people about the integer quantum Hall effect, they think about free fermions. There's no fractional charge, there are no fractional statistics. We could write down a wave function that involves non-interacting electrons, some Slater determinant. And if you add in disorder, the disorder is crucial for having a range of magnetic fields where you have a quantum Hall phase. What you find is that you're solving the problem of non-interacting electrons in a magnetic field. So there's Landau level quantization, and there's disorder. And that problem has been studied ad nauseum. And what we know is that all of the wave functions are exponentially attenuated, also known as localized, generically, except at one energy shown by this vertical line, where the wave functions are delocalized. And those are the wave functions that are predominantly current carrying states. Okay, so as you change the magnetic field, what happens is that the chemical potential varies and grows because, as you increase the magnetic field, the number of states in the Landau level increases, and eventually the Fermi level decreases because we have a constant density. It decreases and crosses from these localized states to an extended state back to the localized states. And that's the spectral perspective of this quantum Hall transition. Okay, so we change the number of Landau levels, at least the extended states that we fill. Complementary view to all of this is a real space picture where we think of droplets of quantum Hall states, say an integer quantum Hall state at filling fraction 1. Nu denotes the filling fraction, the ratio of the electron density to the flux density. And then there can be in a background of nu equals 0 or insulating state. And as you change the magnetic field, the relative volume of these puddles of quantum Hall state change relative to the background. So you can think of them as islands in an ocean. People have these very vivid pictures. In one phase where the ocean dominates, you have the quantum Hall state, say, or in the other state where the islands dominate, you have the insulating state. And at the critical point between these two extremes, there's some percolation of these droplets. Okay, and this is known as a network model pioneered by John Chalker and Coddington. All of this is to say that we think this phenomenon is free fermion physics, even at criticality. By contrast, if I asked anyone in their right mind about the fractional quantum Hall effect, nobody would say that this is free fermion physics, right? Because we have Laughlin quasi-particles that have charge 1/3, say there's topological order, ground state degeneracy. None of this happens with free fermions. So when we think of phase transitions involving the fractional quantum Hall state, nobody would say that this is non-interacting physics. And yet most people would say that the integer transition is non-interacting physics. So if you accept this very naive and what I'll convince you of as wrong proposition, then you would definitely have to conclude that the phase transitions involving the integer quantum Hall state are distinct in terms of the universality class of the phase transitions involving the fractional quantum Hall states. Well, that turns out to be an incorrect argument. The reason is, the fallacy in this reasoning is that the integer quantum Hall states, even though they are adiabatically continuable to free fermions, the phase transitions involving them are not free. Okay, the adiabatic principle, of course, breaks down at a critical point. And just because phases on either side are free doesn't mean that the critical phenomena has to be free. In fact, there's very good reason to think that the phase transitions, even of the integer states, are not free. And therefore, since interactions are important for both the integer and fractional quantum Hall transitions, there's the chance that both may be in the same universality class. And this, if true, is known as superuniversality, okay, in the context of quantum Hall effect. That the integer quantum Hall transitions and the fractional quantum Hall transitions are the same universality class. All right, so now let me, yes.
I'm sorry. I mean, just on the basis of simple pictures, if you think of this percolation of electrons between different islands, okay?
Correct.
I think from this point of view, the fact that fractional and integer is the same is not totally, I mean, is reasonable, because the fact that the electron is split in several fractional excitation, this is true inside one droplet. When you move from one droplet to another, it's clear that that should be an electron. So if you want to discuss the tunneling of electrons of excitation from one droplet to another, it seems to me that even if inside the droplet it is fractional, when it tunnels to another droplet, it should be an electron. So from this point of view, from this simple picture, it's fine for me that that free electron system applies to both transition between fractional and integer plateaus. Am I wrong, or what?
Yeah, well, so I would say that I would disagree with that, just because, you see, there's been no way of incorporating interactions. You need interactions even within the green region, say. If you want to have a fractional quantum Hall droplet, you need interactions within some, perhaps maybe short distance droplet regime to incorporate the fractional statistics. And there has been no incorporation of interactions in this network model. And certainly as the droplet size grows, the region in which you have to include interactions grows, especially in the vicinity of the critical point. Right? Now, your intuition is the right one, in my opinion, because there is a representation in which what you say is correct. And that's the way to think about the superuniversality. And that's really the point of my talk. So that's a good question. Okay, but I want to tell you why this free fermion perspective leads to some very basic problems. Okay, have I addressed your question? By the way, who am I speaking to? Okay, all right, I'll go on.
Okay, please go on. I am Andrea. Okay. Please
oh, Andrea. Okay, good. Okay. All
Yes.
right, thank you. So here's one basic issue. You know, experiments, much to our dislike and inconvenience, are done at finite temperature. And when we measure the resistance, when the experimentalists measure the resistance in the vicinity of a quantum Hall to insulator transition, which they do at finite temperature, what you find is that the resistance, the DC resistance, is finite. In fact, it's of the order of the quantum of resistance. It turns out that if you were a principled person and computed the resistance in a non-interacting model, you would get 0 at any finite temperature without interactions in this problem. The reason for that is there's a well-defined order of limits for computing the resistance or the conductivity, DC conductivity. You imagine a system at finite frequency, finite temperature, and finite size, and you take the following order of limits. You first take the thermodynamic limit, then you take the 0 frequency limit, and then you take the 0 temperature limit. If you interchange any of these limits, you get different answers. So this is a very delicate thing. So if you do it right, if you don't include interactions, you get 0 at finite temperature. If the interactions were irrelevant and vanished at the 0 temperature critical point, that's okay. But at finite temperature, they're still non-zero and have to be incorporated. Okay, so what that means is that even irrelevant interactions must be taken into account to get something so basic as the observation of a finite resistance. And this is not a small effect because, you know, the resistance for the quantum Hall to insulator transition is the quantum of resistance, h over e squared, which is about 26 kiloohms. So, and that's observed. So what I'm showing here are a bunch of curves at different temperature known as isotherms. And the isotherms cross right at the quantum Hall to insulator transition. And if you look at the intercept of the resistivity, where they cross, it's pretty close to the quantum Hall, the quantum of resistance. So why can't you get this from free fermions? It's because the energy at the states which contribute to transport and conductivity occupy a set of measure 0. They only exist at one energy. This is the density of states as a function of energy, and the Landau level with disorder. So when you sit at exactly, if your Fermi level is right at the extended energy, you know, but if you're at finite temperature, states within a width of the order of K Boltzmann times the temperature will contribute to any observable, whether it's conductivities or otherwise. And since the extended states occupy a set of measure 0, they contribute in finite temperature to nothing to the DC transport. Okay. So that's one basic issue that requires the use of interactions. The second is the notion that this is a quantum phase transition, which has you know, there's a continuous nature to it. So there's a length scale and a time scale that diverges, and the way in which the time scales diverge relative to the length scales are known as dynamical scaling. There's an exponent nu associated with the length scale. In this context, it's not the correlation length. There's no order parameter for these problems. There's something known as the localization length, which diverges as the field approaches the critical field with some universal exponent nu. And the time scale associated with it diverges with some dynamical exponent z, defined here. And you know, you can measure these in experiments. For instance, the resistivity, where in 2 dimensions, the resistivity has the same units as resistance. And so at criticality, this resistance as a function of magnetic field and temperature is just some number, some universal number, times a scaling function that depends only on the ratio of some dimensionless tuning parameter to the temperature to some exponent. So if you measure the resistivity and do a scaling collapse, you can in principle obtain nu and z. Secondly, if you look at nonlinear response, so the fact that the electric field has an energy associated with it. Remember, in electrostatics, the energy is the charge times the electric field times the length. And so the energy knows about lengths, and it's an energy, so it knows about times. So there's a scaling form for the nonlinear response due to an electric field. And that goes like the tuning parameter to the electric field to another exponent, 1 plus nu z. So with these 2 sets of data points and scaling collapse, you can obtain nu z and nu independently. And therefore, you know nu and z independently. And what's found for a class of phase transitions, integer quantum Hall and fractional quantum Hall transitions, is that z, first of all, is 1. And the exponent nu is about 2.3. Okay, so they all seem to have similar exponents. Now, if you thought about non-interacting picture of this problem, if there are no interactions, the only way energies depend on length is through the density of states, because the density of states is a number per unit energy per unit volume. So you always get from that picture, as long as the density of states is not diverging or vanishing, the density of states being finite sets the dynamical scaling laws to be z equals d. And since we're in 2 dimensions, z would be 2. So there you go. There's 2 reasons why interactions are important. First, the very basic observation of a finite temperature DC resistance. And second, the observation of dynamical scaling laws that are inconsistent with free particles. So in the 90s, when people were actively working on this problem, there was a hand-waving argument for why z is 1. Well, you say there's Coulomb interactions, E squared over R, that's an energy, and there's an energy that goes like 1 over length, so that's a fast hand-waving argument for why z is 1. But what this suggests is that you need interactions to get z equals 1. What I will provide for you is a slightly more sophisticated argument for how you get z equals 1 by thinking about the problem in a different coordinates system. Okay, but what I want to show you is that so far, all I've told you is that you can't think of many universal aspects of this problem cannot be understood without incorporating interactions and certainly disorder. So that's one of the annoying aspects of this problem. You need to include disorder and interactions. But on the other hand, so it's aesthetically perhaps unpleasing. But on the other hand, both of those features, interactions and disorder, enable a universal description. Without either, you would not have the universal physics. And so they're crucial elements of the problem. Okay, so now let's talk about one last thing before I go on into motivation. There was a nice review on the subject in the early or late 90s by Steve Gervin and Shivaji Sondhi and Dan Shahar and others. And at the end, they outline some open problems in the subject. They say, quote, z equals 1 strongly suggests that Coulomb interactions are playing an important role. And then they say, the a priori validity of superuniversality is still unclear. Okay, so superuniversality, again, is the notion that fractional and integer transitions have the same exponents. And then they say, in summary, theorists have their work cut out for them. Okay, unfortunately, not much has changed since the 90s, but I'm hoping to revitalize the subject and get back to it because it's such an interesting problem. So the theory is still in a primitive stage. That's because we neglect interactions. You need them, in summary, for finite DC resistance. You need them for the correct dynamical scaling laws, and you need them to compare fractional and integer phase transitions. And the real punchline of my talk is that if you work in a different coordinate system, motivated by duality, and you go into composite fermion coordinates, you readily can access these 3 questions. We haven't fully solved the problem yet. I cannot compute the localization length exponent nu, but I know how to do it. And given the right labor accessibility, I think I plan to do this in the near future. All right, so any questions before I move on? So far? Okay, I'm going to move on then. Just interrupt me at will, please. So in the original coordinates of the experimentalists, here's the problem we want to solve. We have electrons, a destruction operator C, in the presence of a magnetic field, a vector potential whose curl is big B. At finite density, there's a chemical potential. These are non-relativistic particles. Well, at finite density, you've already broken Lorentz invariance, and a magnetic field breaks it, so that's fine. But in addition to this, we must include disorder in the form of a random potential, V of R, that's just a static potential, it's not dynamical, coupled to the density, and interactions, which are of the form of density. Okay? This is a hopeless problem. There are no small parameters. There's no way to solve this problem except by guessing the answer and invoking your genius. But while that may have worked for the phases themselves in uncovering the quantum Hall effect, critical phenomena is a very different problem. It's much harder than understanding the gap phases of matter. So we want to do something else. And what I want to do is change the coordinates, as we often do in physics. When we have a hard problem, we change coordinates and where things look maybe easier. And so we have 2 choices of coordinate transformations. One both of which are known as composite fermions, which I'll just briefly touch on as we go on. There's two choices of the theory. The first is the idea pioneered by Bert Halperin, Patrick Lee, and Nick Reed back in the 90s. And it basically takes the electrons, you do a singular gauge transformation on the many-body wave functions, and this is known as flux attachment, and it motivates a different approach to the problem, different set of fermions which carry both charge and flux, two flux quanta in this case, known as composite fermions. And then there's a way of which, that's a strongly interacting problem. Those fermions are coupled to a dynamical gauge field. There's interactions mediated by the gauge fields in disorder. But there's a new mean field-like approximations that these things motivate, where you smear the flux and make it uniform and look at fluctuational corrections of the gauge fields. So this is the program of flux attachment, and it's been tried for many, many decades, and lots of papers exist on it. The second composite fermion theory was pioneered by Son recently, and I assume you've had some talks on this in your program in this meeting. And this is an approach that I prefer. It's basically a particle vortex duality transformation of the 2 + 1 dimensional electron problem, in which the composite fermions are kind of like fermionized vortices of the electrons. Like in a superconductor, you have Cooper pairs and vortices. This is a sort of fermionic analog of that, where the original electrons have a vortex in their wave functions, in their many-body wave functions, and those vortices are composite fermions, and vice versa. So the electrons are vortices for the composite fermions, as is always true for particle vortex duality. Now, both of these theories will motivate some traditional mean field plus fluctuations approach. I say traditional because that's what we do in statistical mechanics. If we worked at electron coordinates, we just need, maybe Bob Laughlin to solve the problem for us. But if we worked in this dual representation, we can take on our statistical mechanics approach, try an approach where we ignore fluctuations first, get a set of conclusions, and then include fluctuational corrections in a hopefully controlled fashion. So that's what I've done. I've conducted a mean field and a fluctuational analysis. And the conclusions of this are that in the mean field approximation, both of these theories, 1 and 2, lead to identical predictions. But interestingly, in an interesting way, actually, the two theories differ once you include fluctuations. And I will talk about how that happens. So just for some of you who haven't seen this before, let me motivate this Dirac composite fermion approach to the problem. There's many ways of doing it. The simplest and quickest way to do it is to note that if you look at electrons, non-relativistic electrons in the lowest Landau level, and you look at their wave functions, you pick your favorite gauge, it doesn't matter. The wave functions are identical to those of Dirac electrons in the lowest Landau level, up to a spinor structure. Okay, so the Dirac electrons in the lowest Landau level have a spinor, but only one component of the spinor is occupied. So it's almost identical to a spinless non-relativistic electron in the lowest Landau level. Okay, so since the wave functions are the same, you can add disorder and interactions in many of the same ways, and they behave identically. So in the spirit of doing critical phenomena, where we're looking at only universal properties, it doesn't really matter whether we consider Dirac electrons or non-relativistic electrons. Okay, but one nice thing that was noted by Son is that if you take the lowest Landau level limit, where the magnetic field is infinitely strong, the particles, since the cyclotron energy is the magnetic field divided by the mass, one way of taking the lowest Landau level limit is to assume that the mass of the electron goes to 0. And that's the essential motivation for thinking of Dirac electrons in a magnetic field. Okay. But for our purposes, just think of this as a UV regularization of the quantum Hall effect, where we have electrons, Dirac electrons, with some coupled to an external magnetic field. And then there's the method of going to a different coordinates known as particle vortex duality, where we go from electron coordinates to these Dirac composite fermion coordinates, which are denoted by psi. And these Dirac composite fermions don't directly covariantly couple to the background magnetic field. They instead couple to a dynamical U1 gauge field denoted by little a. And the U1 gauge field, unlike electromagnetism, lives in 2+1 dimensions. Of course, electromagnetism lives in 3+1 dimensions. And it's also fluctuating, okay? It's denoted here. Now, if you look at, since these two Lagrangians are supposed to produce the same predictions, you can look at the definition of the currents in either of them. If you use the dual theory, you find that the electron density obtained by differentiating the Lagrangian with respect to the background fields is set by the difference between the background flux and the dynamical flux, okay? Big B is curl of big A, and little b is curl of little a. And by contrast, the dynamical gauge field, so the composite fermion density is set by the only external magnetic field. And if you think intuitively in terms of vortices, think of a superconductor. If you apply a magnetic field, you'll generate some field-induced vortices. The composite fermions in this theory are sort of field-induced vortices of the electrons. All right, so to this theory, to the dual theory, I want to now add disorder and interactions. And I'll first start by adding disorder. In electron coordinates, we add a random potential, and that can be done by shifting the background time component of the vector potential, the scalar potential, to include some spatially varying piece, V of R, which is like a random chemical potential. Okay, so in the electron coordinates, that shifts the Lagrangian. There's a clean piece and a disordered piece, and the disordered piece is just the density coupling to the random potential. Now we want to dualize this and think of the same disorder in the dual representation. Okay, again, we shift the capital A, the time component, to include a quenched random potential. Now, since the dual theory involves vortices, if you have a random potential for electrons, you're going to have some regions where there's more electrons than others. But since the electrons act as vortices for the composite fermions, that induces a random flux, okay? But these are words, but this can be made precise by noting that there's a cross-Chern-Simons-like term. If you add a time component to it, you're going to have you're going to source a dynamical flux in the disorder theory, okay? So whereas the original disorder theory had a random potential, the dual theory has a random potential that sources the flux. Okay, so now we have a dynamical flux that has a quenched piece and a fluctuating piece. Okay, since B is curl of little a, the way you implement this in the Lagrangian is to couple the Dirac composite fermions to a random vector potential. So remember, little a is fluctuating; it's a dynamical field, but you can break it up into a fluctuating piece and a quenched random piece. And the quenched random piece has a curl known as B of R. Okay. So I've already said this in words. So instead, a random magnetic field implies a random chemical potential, and this fluctuating gauge field, we have a path integral over configurations of this fluctuating gauge field, can be written as can be shifted with respect to this quenched random piece. The quenched random piece is obtained from some probability distribution, say the Gaussian probability distribution, and that's how we imagine including disorder in the composite fermion representation. Is that clear to everyone?
Yes, please keep going.
Then we talk about interactions. So this is where now the composite fermions start to shine relative to electrons. So remember, in electron coordinates, we have some density-density interaction. We can specify what U of R is in a minute. But the point is there are 4 fermion interactions. This is C dagger C, that's C dagger C. That makes the problem complicated in the Landau level representation. But in the composite fermion, the dual theory, the fluctuational correction, the variations in the density are equivalent to the variations in the flux. So this is a flux-flux interaction in the dual frame. But since B is curl of A. This is just quadratic in the dynamical gauge fields. Okay, so this is some new gauge boson kinetic term, quadratic in A. That's how interactions are incorporated. So for instance, if we pick a Coulomb gauge where there's the fluctuating gauge field has a time component denoted A0 and a purely transverse piece denoted A capital T, the interactions only involve the transverse pieces of the gauge field because the magnetic fields only involve the transverse piece. So for instance, for the case of Coulomb interactions, the transverse gauge boson kinetic term has a mod Q in front. And for contact interactions, say delta function, there's a Q squared. Okay, so that's how we incorporate interactions. So to sum it up, we have Dirac composite fermions, a faithful capturing of the quantum Hall physics and the critical phenomena is a composite fermion in the presence of randomness, where the random potential is manifest as a random vector potential. And we have interactions, which is some kinetic piece for the transverse gauge boson. And it's important to note that we're at finite density. So we have a Fermi surface in the absence of disorder.
Excuse me, please.
Yes, please.
But in the composite fermion Lagrangian, you have this term. Can you go to the previous transparency, please?
Yeah.
This term 1 over 8 pi ADA, this is to cancel the anomaly, right?
Yes.
Shouldn't be in this case with little a, not big A. Because you cancel the anomaly due to the coupling of the fermion to the little a field.
I will do that in a second, but this Lagrangian as written is correct. I will show you what we'll do. Okay, I know what you're getting at, and that's an important point. But this is actually, if you include the disorder and interaction Lagrangians, this is as formulated the theory of dual composite fermions. Okay, but let me address your point in a second.
Okay. Sorry.
Yeah, it's a good question. So in this representation, we have, conventional statistical mechanics. We do mean field approximation first, and then we include fluctuations. So I'm going to start with the mean field theory. Well, so how do we do mean field theory? Every fluctuating field's correct contribution to the critical phenomena is only via its equations of motion and nothing beyond the equations of motion. And that's what we mean by mean field theory. But, before I do that, I'm going to address the question that was just asked. Take this Lagrangian and make sure I have, as a condensed matter physicist, I almost always imagine putting things on a lattice where I can tell a computer how to do things. We will get to computing in a second. So we want to understand how to UV regularize the theory, right? And because these are Dirac fermions, they have a parity anomaly, and that has to be dealt with properly. And so what you do is you simply add and subtract one term. So here is the Lagrangian. Ignore the disorder and interaction piece for the moment. It has 3 terms. And what we can do is write those 3 terms as a piece that involves a UV regularized fermion theory and a sector that involves only the gauge fields fluctuating in background. Okay, so we can subtract and add this minus 1 over 8 pi ADA, the half Chern-Simons term. And so the first piece looks like this, and the second piece looks like this. Okay, now this Lagrangian now is a UV complete Lagrangian because it involves a Dirac fermion, which is massless, and say another massive, from the doubler fermion. If we put the system on a lattice, there will always be a doubler fermion. And if we give that fermion a big mass, say big compared to the chemical potential, this, when it integrated out, will generate, in addition to irrelevant couplings, the half Chern-Simons term. By the way, for those of you who don't like this improperly quantized Chern-Simons levels, I would be one of them. I would say that you can easily fix that by including additional gauge fields. I'm not interested in that today because I'm not interested in any global property. I'm only interested in local degrees of freedom. So we could just put this on a torus and not worry about anything, or just on a plane rather. Okay, So having obtained a Lagrangian that's UV complete, so there's a fermion, a matter piece, a Dirac fermion with its massive partner, and a gauge sector, the Lagrangian is now associated with a properly regulated, regularized Hamiltonian. Okay, so the matter part, L psi, is associated with a Hamiltonian, H psi, which has two pieces, H1 and H2. And these are two-component Dirac fermions, so you can always write the gamma matrices as Pauli matrices. The first Hamiltonian involves the massive degree of freedom. So there's a massless degree of freedom. There's a massless Dirac fermion at finite chemical potential. And the second term involves the massive partner. So the precise value of the mass doesn't matter as long as it's big compared to the chemical potential so that it doesn't cross the Fermi level and give rise to gapless modes. So this is just the properly regulated theory. Now, how does the mean field theory know about the quantum Hall to insulator transition? Well, it's a very elegant story, actually, because as you all know, the Dirac fermion in a magnetic field has the property of these topological modes known as zero modes. The number of zero modes that are present are given by the number of flux quanta in an externally applied magnetic field. So what I want to do is imagine taking the massless Dirac fermion, and remember, this is the fluctuating gauge field in the mean field approximation. We only treat its fluctuations at the equations of motion level. But we have disorder. So there's a random piece, which I called earlier A prime, whose curl gives rise to a random magnetic field. This random magnetic field can have non-zero average or zero average. It turns out the average component of the magnetic field is the tuning parameter for the quantum phase transition. When you look at a non-zero average flux, external flux for these Dirac fermions, the density of states looks like this. There's some set of states at finite energy, and at zero energy, there's some sharp set of zero energy modes, the number of which is given by the number of flux quanta of B naught. Okay, so what this means is, if you look at the Hall conductance, the zero modes act like a Landau level. But since they're at zero energy, and since this is Dirac fermions, they are exactly half filled, right? So they only contribute half Hall conductance. And the magnitude of the Hall conductance, or the sign of the Hall conductance, depends on the sign of the magnetic field, as you all know. Okay, so the zero modes are either seeing an external magnetic field, which could be positive or negative, and so the Hall conductance can be positive or negative, but it's half in units of E squared over H. E squared over H in the canonical units of theorists is 1 over 2 pi. So this is half of the Hall conductance. So what this says is that for B naught, the average curl of little a, being positive, you get 1 over 1/2 Hall conductance, and for B naught negative, you get minus 1/2 Hall conductance, okay? But then if we include H2, the massive partner, which is just a background, always generates a static minus 1/2 contribution, then we see that for one sign of the magnetic field, the Hall conductance is 0. Say for B naught less than 0, it's an integer quantum Hall state, and for B naught greater than 0, it's an integer, it's an insulator. Okay, so this is how the mean field theory captures the integer quantum Hall states, integer quantum Hall to insulator transition. Observe that the electrons undergoing an integer quantum Hall to insulator transition in composite fermion representation is also an integer quantum Hall to insulator transition of composite fermions. Okay, so this led me to think some years ago that maybe the transitions are self-dual, because in both coordinates, the phases of matter are integer quantum Hall or insulator. Although the precise Hall conductance of electrons and composite fermions are different, the phases nonetheless seem to be reminiscent of one another. Therefore, maybe the critical point is self-dual. But I won't talk about that so much today. What is important in this talk is what happens at criticality. Notice that at criticality, there are no zero modes, right? There's this average magnetic flux faced by the composite fermions is 0. So the light Dirac fermion starts to enjoy a time reversal invariance at criticality when the average flux vanishes. Well, this is not strictly true. There's a random magnetic field, so that breaks time reversal. But on average, when you disorder average, there's a time reversal symmetry, right? So what that implies is that the light fermion contributes nothing at criticality to the Hall conductance. And the entire Hall conductance is obtained from the anomaly canceling massive partner, which is -1/2 at criticality. Now, this has profound importance because if we go back to the old days of the quantum Hall effect, the early days, there was this beautiful argument by Bob Laughlin, which goes something like this. It's known as the gauge argument. And what he taught us was, he said, if the states at the Fermi level are localized, sigma xy, the Hall conductance must be 1/2 pi, or e²/h, times an integer. Well, the contrapositive of this argument says that if sigma xy is not an integer multiple of 1/2 pi, in our case, it's a half of that, the states cannot be localized. They must be delocalized at the Fermi level. Now, I could have put the Fermi level of composite fermions anywhere here. It could be any positive number. What this says is that states must be delocalized no matter where the Fermi level is, which means that all states at all energies at criticality, states are delocalized in this theory. Go back to the electron representation where there's only one energy at which states are delocalized. In the composite fermion, the dual representation, all energies at criticality are delocalized. And so now there's no subtlety. You can work at finite temperature in the mean field approximation, and you'll find a finite DC resistance even at finite temperature for the composite fermions at criticality in this representation. So that's a huge advantage to the composite fermion representation. It sort of incorporates the electron-electron interactions in a clever way and enables you to realize a finite DC, finite temperature transport. So now, if you go back to, there's a dictionary relating linear response of composite fermions and that of electrons. Basically, the intuitive picture is this. If you have electrons moving down, if you apply drive a current, electrons moving this way. In the dual representation, you can think of the composite fermions moving along the current, and they are like vortices, right? So every time they move, there's a phase slip. The phase slip of their wave functions produces a Hall voltage transverse to their motion. And we can be more precise. I'm just being very cartoonish. At the end of the day, if you integrate out the dynamical gauge fields, integrate out the composite fermions, and map linear responses across the dictionary of duality, you find that the composite fermion resistivity tensor is the electron resistivity tensor plus 4 pi times the unit antisymmetric tensor, epsilon AB. So the point I'm making is that while it was by no means obvious that non-interacting electrons have a finite temperature DC transport, it's obvious in the composite fermion representation because there's extended states over a broad range of energies. So you obtain a finite rho CF, and then you use this dictionary to get a finite rho electrical resistance. Okay. Again, this is not obvious in electron coordinates where there's only one energy of extended states. But in composite fermions, I would say the composite fermion dual representation, the existence of it justifies the observation of a finite temperature DC transport. Now, because one proof that you know what you're talking about is you could tell a computer what to do, and we exactly did that. We simulated, we studied the composite fermion theory numerically, basically this Hamiltonian. We put it on a computer, worked out different disorder realizations. At mean field theory, you can ignore gauge fluctuations, so it's a free fermion problem. And you can obtain the critical exponents, and we obtained this. And what we found was that we got a value for nu, which was 2.56. It's in excellent agreement with the Chocker-Coddington model that was formulated in electron coordinates, this percolation of puddles that I mentioned. And there's other attributes of the critical point, which are known as wave function multifractality. I'm not going to go into that. Basically, as you know, at any critical point, you need two critical exponents. One is nu, and the other one is sort of like a wave function, an anomalous dimension of the fermions. And this is known as multifractality. And this is also an excellent agreement with that of the Chalker-Coddington model. So what this tells you is that the mean field theory is correctly formulated. And we can go beyond this now and look at fluctuations. But before I do that, this is the point at which the composite fermion theory shines beautifully. Okay, so we talked so far, everything I told you was the integer problem. Now we can go into the fractional quantum Hall problem.
There is a problem. There is a question, sorry.
Please. Yes. Question, go ahead.
Yes, hello. I have the following question. So what was the role of disorder so far? You said that there is a random background component of this magnetic field.
Yes.
Statistical one, but it did not play a role so far, at least naively. You just said that it's used to be localized, now it's localized, but where is exactly you use interactions with disorder?
You mean disorder?
Oh, sorry. No, actually I meant interactions, this U.
Yeah, so that will play a role when you include gauge fluctuations. I haven't gotten to that yet.
So interactions did not play, okay.
Nothing yet.
Thank you.
Yes, good question. All right, so here's where the problem is fantastic, okay? So if I wanted to go from go from integer quantum Hall to say the fractional quantum Hall transitions, the abelian fractional quantum Hall states, where say nu equals 1/3 to 0 transitions. That's just these set of filling fractions, 1/2m minus 1, with m equals 1, 2, and 3, and so on. All we need to do is change one parameter in our composite fermion Lagrangian. So the composite fermion Lagrangian has a matter piece and a gauge piece, disorder and interactions. The matter piece is identical to before, and the gauge piece has this m in it. Okay, so this is the generalization of Son's composite fermion theory at other fractions, not just 1/2, but 1/4, 1/8, and so on. These would be the critical phenomena for the 1/3 to 0 transition, or the 1/5 to the 0 transition, and so on. But what I want you to observe is that the fermion sector is unchanged. These composite fermions are absolutely unchanged. The only place where m, the data of the fractional quantum Hall state, go in is into the gauge sector of the Lagrangian. So if we're doing mean field theory, we expect the critical exponents to be the same for the abelian fractional fractions and the integers. But this is a trivial form of superuniversality, not the kind that I want to advocate in this talk. To establish the superuniversality, you have to go beyond mean field theory and actually include interactions in the form of gauge fluctuations. Let me give you an analogy that might be helpful. When you study in statistical mechanics or quantum field theory, the Landau theory of phase transitions, the Landau theory of phase transitions, when you ignore fluctuations, thermal fluctuations, are super universal, right? It doesn't matter if I'm studying the Ising model, the XY model, the Heisenberg model, the ON model, they all have the same critical exponents at mean field, right? If you want to include changes in, if you want to deduce changes in the critical exponents, you need to include fluctuations, say Phi-4 theory in the epsilon expansion or something like that, or 1/n. So far, the observation that the integer and fractional quantum Hall states are in the same universality class, because the fermion sector is the same and we're ignoring gauge fluctuations, is exactly analogous to that sense of super universality of Landau theory. But we have to do better than that. Okay, and I should say this was the status of the literature before we did this work. So I think we've made an advance here. All right, so at the end of the day, the only thing that changes with integer versus fractional transitions in the mean field limit is the universal resistance at criticality. It knows about the data of the filling fractions, okay? But all the other exponents are the same as the integer quantum Hall effect. So my main message so far is that at criticality, the composite fermions have a finite conductivity. The transitions as viewed in this composite fermion mean field theory are trivially superuniversal. While the conductivities are different, the localization length exponent would be the same. the wave function multifractality would be the same, but the dynamical exponent would be 2 because it's set by the density of states, not by any interactions. So now I want to take the leap forward and include interactions in the last, alas, 5 minutes of my talk. Okay. So, I wanted to give you a roadmap in case I didn't finish. So I'm glad I did. So here's the argument that I want to take you through. The key points is that with interactions and with disorder, the composite fermions will have a finite non-zero DC conductivity at the critical point. They will also have a finite static compressibility at the critical point. These 2 points are crucial because the first one establishes the dynamical scaling relations, as you'll see, and the second establishes the superuniversality of the transitions, at least with 1/r interactions, where fluctuations are treated as well as disorder. Okay, so to establish 1 and 2, you have to average over randomness, and the effective field theory that knows about the averaged quantities is, in this context, a nonlinear sigma model. It's gauged because there's a dynamical gauge field, so the sigma model fields are coupled to the gauge field. And in addition, there's a theta term, a topological term. So this is a difficult theory to work with. We can't compute with it because it flows off to strong coupling. But nonetheless, without doing any calculations, we can exactly be confident in 1 and 2. So here's how we do it. We start with the integer states, okay? We have the matter piece, the gauge piece, the disorder piece, and the interaction piece. The interaction piece is this, and the gauge piece is this. So what we want to do is average over randomness with respect to some probability distribution, and that's done using standard techniques known as the replica method, which this audience is, I'm sure, familiar with. And when you do that, you replicate and you integrate out the disorder, you obtain an effective field theory where the action consists of a gauge, the action associated with L gauge, the interaction piece, and a piece that involves these new degrees of freedom known as the Q fields. Okay, these are the nonlinear sigma model fields. And these are somewhat off-putting, they're a little ugly, but they are matrix fields that know about replica labels, A and B, and 2 time labels because the disorder problem is static in time. You can work in a Matsubara frequency representation. In imaginary time, you have a finite temperature. You can, the frequency modes are discrete. They're known as the Matsubara frequencies. So these matrices have 2 labels, replica, Matsubara frequency labels, and space. They live in space. They don't live in time, they live in space. Okay, so they live in 2 + 0 dimensions. And that's important because the 2 + 0 dimensional theory, as you know, has anomalies, the chiral anomaly, and that anomaly can give rise to theta terms, which we actually explicitly computed in our theory for the nonlinear sigma model. Okay, I'm gonna now go a little fast because I realize I'm running out of time. I just want to say the strategy for computing. Okay, this theory, as written, is exact. Okay, you integrate out the disorder. There are these Q matrices and there's gauge fields. And what we want to do is analyze this theory now in the following approximations. First, there's a saddle point of the sigma model fields. And then there's an expansion in powers of the gauge field. The gauge field coupled to the Q matrices is in this form. Basically, its form can be deduced simply from gauge invariance, nothing else. Okay? And the Q fields live in this Grassmannian manifold of U2n mod UN times UN. And again, this is the replica theory, so we take the n goes to 0 limit. The effective field theory for the saddle point, ignoring gauge fluctuations, the coupling to the gauge fields, is just a nonlinear sigma model with a topological term whose coefficient is the Hall conductance. And the expansion about in powers of the coupling to the gauge field is just going to be deduced by gauge invariance. And it has this form. Now, I don't expect you to understand what I'm talking about right now, but there's one thing that I want you to take away from this. Notice that the couplings between the Q fields and the dynamical gauge fields only involve sigma xx. Okay? They do not involve sigma xy at the critical point. What that means is that since sigma xy is the coefficient of the topological term, it's exactly unrenormalized by gauge fluctuations. This is true to all orders in no matter what g. You can set g to 1, and we can say this exactly true. This is exactly true. And the reason for this is a very simple and intuitive physical argument. The topological term is related to sigma xy, right? And in the Dirac composite fermion theory, the only contribution to sigma xy come from the anomaly canceling massive doubler modes. They're far away from the Fermi level. They're not gapless degrees of freedom. They don't know about the disorder. They're purely topological. And so their contribution to the Hall conductance is entirely independent of gauge fluctuations as well. Because they're massive modes, you can just ignore the gauge fluctuations in their sector. All the light degrees of freedom at criticality enjoy a time reversal invariance. There's no mass term at criticality. It's been tuned to 0. And so that implies that they can't contribute any Hall conductance. This light Dirac doesn't contribute any Hall conductance. And so since the light Dirac is the one that's encountering gauge fluctuations, this theory has a beautiful property that at criticality, gauge fluctuations do not change the DC Hall conductance. I should just say in passing that the non-relativistic HLR type theory does not have this feature. So this is where the two composite fermion theories differ. The HLR theory has its Hall conductance entirely from gapless modes at the Fermi surface. So now when you include gauge fluctuations, the theta term, the Hall conductance, the topological term, will be renormalized by gauge fluctuations. So that means that the Hall conductance at criticality is a running coupling in this theory, but not in the Sans Dirac composite fermion theory. Okay? What does that further imply for us? The implication that sigma xy doesn't run, it's fixed by a half integer multiple of e squared over h, means again by Laughlin's gauge argument that states at criticality must be delocalized. If they're delocalized, what the gauge fields will have is a source of dissipation from these delocalized states. And furthermore, since there's a finite density of states of these delocalized states, we have the phenomenon of Debye screening. Okay? And let me explain what this means. So this is how we deduce superuniversality. Okay? The finite density of states at criticality makes the composite fermions having a finite compressibility. Okay, so this is just the Einstein relation between the density of states and the compressibility. What this tells us immediately is that the Chern-Simons terms, which know about which fraction we're talking about, whether we're talking about integer states or fractional states, are included in the Chern-Simons term. But what this will become is irrelevant. So that's the way in which we see superuniversality. So all the data about integer versus fractional is incorporated into an irrelevant operator at criticality. Here's how it comes about. So the finite compressibility looks like a mass term for the temporal piece of the gauge field. Then there's the Chern-Simons piece, okay, which knows about integer versus fractional. It's a cross term between the temporal and the transverse gauge field. And all the interaction pieces, say for Coulomb interaction, there's a Q linear term, involves only the transverse gauge fields. Okay, so since there's a mass-like term for A0, you can integrate it out. It's massive modes. You integrate it out, you get a renormalization, a theory that only involves the transverse degrees of freedom, which knows about Coulomb interactions, and all the Chern-Simons data about fractions versus integers is subleading. Okay, and since it's subleading, it's irrelevant. And since it's irrelevant, integer states and fractional states have the same universality class. Okay, if there are questions about this, am I violating gauge invariance? You can ask me at the end of my talk. The short answer is no. Everything's fine. Don't worry. Then from this, we can deduce another feature, which is the dynamical scaling laws. Okay, so we say that the interactions is a transverse kinetic term like this. But now, since states at criticality are delocalized, we know that because the Hall conductance doesn't run, it's a half integer multiple. Laughlin tells us that states are delocalized. If states are delocalized, they have a finite DC conductivity. And so since the gauge boson couples to the currents of composite fermions, and since the Kubo formula tells us that the conductivity is the current correlator, which is the quantum correction for the gauge boson, the quantum action for the gauge boson is nothing more than the piece set by the kinetic term, the interactions, and the Kubo formula. And notice that this is exactly z equals 1. So how did we get z equals 1? The finite conductivity giving rise to due to the extended states at criticality in conjunction with Coulomb interactions gives us z equals 1. Okay. So the gauge boson is overdamped by the dissipative modes, and the Kubo formula tells us that the current correlator sets omega and q to be linear relationship to one another. Notice that this is not Lorentz invariant. Z equals 1 doesn't always imply Lorentz invariance. There's an I here. So this is an imaginary self-energy, so that's a source of dissipation for the boson. So nonetheless, this sets z equals 1. And I should say that the result is self-consistent. If you feed this boson back into the fermions, you get exactly a Fermi liquid action with which are delocalized with delocalized states at criticality. And so if you recompute everything, this is going to be self-consistent. Okay, so this is how you see superuniversality and dynamical scaling laws in this representation. I realize that I'm out of time. Let me just say that we can repeat with contact interactions. Then the dynamical scaling laws are z equals 2. Superuniversality is present up to logarithmic corrections. So if we want to compute, how much time do I have left? I guess I'm out of time, right?
Yes.
Okay, so
maybe you should conclude. Yes, please.
I will conclude in 1 minute. So the universal properties of this theory have 3 running couplings: sigma xx, sigma xy, and the interaction strength. At criticality, sigma xy doesn't run, and we only have 2 couplings: disorder and interactions. And even though the theory runs to strong coupling in this phase diagram of these 2 running couplings, we can still be confident that there's a finite DC conductivity and that there's a finite compressibility, which sets the dynamical scaling laws. Okay, so in the future, we can determine the localization length exponent by looking at the gauge boson spectral function with finite sizes and do scaling. But let me just conclude here by saying here's the overall picture. There's interactions, there's disorder. If you neglect gauge fluctuations, you have a theory with z equals 2, but which are super universal in the trivial sense. If you include gauge fluctuations, we immediately see that z is 1, and the theory remains super universal. Okay, and the theme of my talk has been to obtain all of this by going into a dual representation of composite fermions. Okay, so I think I'll stop here. I'll thank you for your time and attention, and for all your good questions.
Thank you very much. Yes. Do you have questions? There is a question. Just a second.
Sure. Whoops. Let me try to open it. Yeah.
Just to be sure I understood. So the claim of superuniversality, can I understand it as saying that there is like one and the same CFT that describes all these transitions, like in a more QFT kind of language, or?
Yeah, yeah, exactly. I don't know if it's a CFT. It's not Lorentz invariant, so it's not a CFT, I would say, but it's scale invariant. It's some scale invariant effective field theory.
Okay. Thanks.
Sure.
Another question.
Sun is rising in California.
Thank you very much for a nice talk. I have the following question. So you mentioned that if interaction is different, then it seems to change critical exponents like z. Right?
Yeah.
So is any evidence for that? For example, in experiments, you can actually change the screening of electrons by choosing the distance to the gate. And
okay, so in gallium arsenide, there isn't any. I mean, people can gate the system and then repeat the experiments. I'm hoping that those experiments can be done. That hasn't been done, but now in this modern era, there's many other realizations of quantum Hall physics, like graphene, for instance, which is easy to do. And so I'm hoping such studies can be done. So indeed, the prediction is that if you screen the Coulomb interactions by applying gates, the dynamical scaling laws as seen in conductivities and electric field response, collapsing of the data would be different, would be 2.
Okay, thank you.
Yeah.
There is another question. Yes.
Yeah.
Yes, I have a very basic question, so probably I missed something. So as far as I understand, the composite fermion model of SON was introduced to describe the quantum Hall state at filling fraction 1/2, which is gapless.
Yeah.
But here, if I understand, you used it to describe integer quantum Hall state, which is capped. So how?
Good question. So at the critical point between the integer state and the insulator, say if we're going from filling fraction 1 to 0, the critical point is at half. You know, it's sort of the gapless point between the two quantum Hall states. So that's the sense in which the composite fermion theory emerges at the critical point. So if you then introduce mass terms to it, you can gap it out in one direction or the other. But at criticality, when the mass terms are tuned to 0, that's the realization of the filling fraction half. Does that answer your question? Yeah.
But so is the statement that this universality class at the transition is the quantum Hall state of filling fraction 1/2?
In the presence of disorder, yes.
I see. Okay, thanks.
Yes. Because the filling fraction half in the clean limit might well be a phase of matter, a stable phase of matter, rather than a point of measure 0 that requires tuning. But with disorder, the statement is indeed that it's a critical point, not a phase of matter. Yeah, other questions?
There is a very old conjecture that there is the modular group acting in the space of the two conductivities that matches the different critical points. This is a very old statement that there are even experimental check of this. So
correct.
My question is whether you can see any signal of the modular group in your theory.
Yeah, so the SL2Z stuff comes out naturally just by doing this thing of relating resistivity, linear response dictionaries to one another. So you know, in the composite fermion frame, you have composite fermions and dynamical gauge fields. So you integrate out the fermions, and then you integrate out the gauge fields at their quadratic term and linear response level, and that relates the background gauge response to the dynamical gauge response, and all of that is exactly consistent with the modular stuff.
So you're saying that as long as you arrive to a sigma model description, then it is built-in.
Yes,
that's
exactly.
That's the answer.
Exactly.
Okay. Okay.
Yeah.
Thank you very much. Okay.
Sure.
Thank you.
See, because that stuff doesn't go into the nonlinear sigma model directly. It's in a separate piece in the gauge action, what I call L gauge. All of that information is there. So, yeah, that's correct.
But you get a normalized value of not of sigma xy, but of sigma xx. You get a normalized value, so that they would violate this symmetry or not.
No, so you know I see the question. I mean, I think the equating of linear response dictionaries suggests that you still satisfy the SL2Z algebra. Whether or not it's exactly true to all orders in gauge fluctuations, that's an interesting question. I thought it would be true, but I'm now that you mention, I have to think about that. Yeah.
Okay. Anyhow, this is a conjecture, and I mean, this just not experimentally completely accessible so far.
Yeah.
So.
But that's something in the composite fermion theory it's easily testable. It's a good idea. It's a good idea. Let's check that. Okay.
Well, so if there are no more questions, we thank again the speaker.
Thank you. I wish I were there, and
okay.
Enjoy your day.
Very nice talk. Thank you very much. Okay.